Hello everyone, welcome to another AP Computer Science video. In this video we're going to continue with even more examples using two-dimensional arrays to practice using them in methods as both parameters and return types. This is kind of the last step of a direct comparison to regular one-dimensional arrays which we've used before. Again, the end goal is the same, but the advantage is we can keep more data, and in certain situations it makes sense to have kind of a grid data set to keep your information and manage it in an easy fashion. I'm going to make a new class just so we can try some examples in our package. I'm going to call this More 2D Arrays. More 2D Arrays. Okay. And so I'm going to go ahead and make a main using my shortcut. And the first example I want to do, and this is a pretty common example and I think a good application of what two-dimensional arrays can do for us. I don't know how much math everyone's taken, but we'll talk about a very simple idea that you might see in some math course, potentially in maybe in pre-calculus. And then, of course, in the future, linear algebra will definitely be a topic where you will see these things. And the idea of a matrix of values. If you've ever seen this, sometimes we have an example of a matrix of values where we might write it something like this. 1, 2, 3, 4, 5, 6. And so this is a matrix. Or another matrix could be something like, I don't know, 1, 2, 4, 7, 5, 2. Something like that, right? So a matrix is basically a grid, a set of rows and columns of values, and you can do different operations, and they might represent things. In real systems, often two-dimensional and three-dimensional matrices represent or are used in linear algebra equations to represent the rotations of 3D objects in space, or the angles or the positions of things in three-dimensional space. And this is a pretty common application in 3D graphics. And even though we're not going to get into that, the general idea, if you look at the picture, is this is essentially a set of rows and columns. And so we can use a two-dimensional array of integers or doubles or anything really to map to this kind of representation. And so one common application, one common theme you might see when you deal with matrices, particularly when you get to linear algebra, is the idea of the identity matrix. The identity matrix is a very simple matrix. Essentially, no matter how many values inside of it, it's always the same. Typically, identity matrices are square, meaning that it has the same number of rows and columns. So in this case, that couldn't really be it, neither could this one. But for example, I could do something like this. 1, 0, 0. The next one would be 0, 1, 0, and the last one would be 0, 0, 1. And essentially, an identity matrix says every value is 0 in the matrix except the left diagonal from top left to bottom right. And so this is a 3 by 3 identity matrix. If I made a 5 by 5, I'll start it because it is going to be pretty big. It would look like 1 and then 4 zeros. That's 1. The next one would be a 0, a 1, and 3 zeros. And you'll notice that the diagonal is going along, and that's 2. The next one would be 1, 2, another 0, 4, and the last one would be 1. Oh, oops. Let's fix this. We'll say 4 zeros and a 1, and that would be the close of our matrix. And again, I didn't really clean this up, but the idea is that that's our matrix, and again, the diagonal is 1s, the rest of them are 0. So any size, if we say it's n by n, then there are n rows and n columns, and the top left to bottom right diagonal is all 1s, the rest are 0s. So we're going to make a method that, given a number like 3 or 5 or 10, generates an identity matrix. That's the first example we're going to do. And so the result is our input will be a single number, like 3, and the output will be a two-dimensional array that represents an identity matrix. So a two-dimensional array of integers is not a bad choice. So let's try doing something like that. So here we go. So we'll make a method. We'll say public, static, and because we're going to return an identity matrix, which is represented by a two-dimensional array of integers, our data type for the return type is integer two-dimensional array. Again, just like arrays, two-dimensional arrays are objects, and they can, even though they are arrays of arrays, they're still a single object. And so we have the ability to create one and return it as a value. Any primitive or class type values. So primitive values or objects can be returned by methods. And so this method generates a two-dimensional array. And so we'll go ahead and call it gen identity. Right, so generate identity matrix. And then the input will be a single number, n, where n is the number of rows and columns we want. So given that n, the first step would be to create the two-dimensional array that's empty. And so let's go ahead and do that. So the data type would be integer two-dimensional array. A name, let's go ahead and call it ident for identity, or whatever you like to call it. And then we need to construct it, so we use our new keyword, just like with any object. And then we must tell it a two-dimensional array, but we must give it sizes. So in this case, again, in our example, it is an n by n. So if n is 3, it's 3 by 3. If it's 5, it's 5 by 5. So our size is n by n. So whatever n happens to be when they give it to us in this method, the resulting two-dimensional array is that large. Now, we save ourselves a lot of work, thankfully, because the default values for arrays, 2D, 1D, any dimension, for primitive integer values or decimal values is 0. So most of the values are already 0, which is convenient. In fact, all of them are already 0. We only have to change a few of them. Our goal is to make that diagonal non-zero, the ones and the ones. And so if we look at this example, if we were to draw indices for each of these things as rows and columns, we would say this is column 0, column 1, column 2. Row 0, row 1, row 2. And if we pay attention to the pattern of the diagonal, notice the first one is at 0, 0. The second one is at 1, 1. The third one is at 2, 2. And the same thing here. This would be 0, 1, 2, 3, and 4. And this would be 0, 1, 2, 3, and 4. And so if we look at the diagonals, the last one's at 4, 4, and then 3, 3, and then 2, 2. So it's really easy to map the diagonal. We can say if we're at row 0 or row I, then we're at column I. If we're at row J, we're at column J. And so the idea is that it's the same. And so in our implementation, we simply need to go through every row and use the same row value, the same row index, as our column index. And that's the value we're going to set to 1. So let's go ahead and do this. We'll say for int I equal to 0, I less than, identity.length. We could also put n. It's also acceptable to put n, so I do this. Because the length is n. We established that it's n. So either way is acceptable. It doesn't really matter which way you choose to do it. Let me go by 1 each time. And I did mention in the previous videos that typically, if you have a two-dimensional array, you're probably going to have a nested loop to fill it in. But in this situation, we don't need a second loop because the I will be both the row and the column. So in fact, it's unnecessary to have a second loop for this because the values happen to be the same. And so we can simply say the identity at position I, row I, column I, is equal to 1. Those are diagonals, and it's that simple. And at the end, what is the last step of our method? Always, if it has a return type, is to have a return statement. Return the identity matrix. And there it is. And this is a situation where we were lucky enough that we don't have to do a nested loop to make things work out effectively. Now we do want to test this method. And so to test it, we have to kind of call the method and generate it, and then maybe display it. So let's make a method that displays matrices, right? It's a convenient thing to do. So I'm gonna make a new method, and we'll say public static void because we're going to print directly. We're not going to return a string. We're just going to print it directly, and we'll go ahead and say print matrix. There it is. And our input is, of course, a two-dimensional array that represents the matrix we're trying to display. And we are assuming integers, so I'll call it matrix. And there it is. And now let's simply go through every row. I equal to 0. And I'll use R and C again. So I'll say R0, R is less than matrix dot length, R plus plus. And then I'm going to go through every column in every row. So this is for every row. And now for every column. Remember, we're saying if I'm in row R, let's get the length of row R. And again, because we can assume it's rectangular. Again, we're going to continually assume that it's rectangular for the sake of the AP exam. Then we could have put 0, but R is fine because they're all going to be the same length. And then we go up by 1 each time. And now here, what are we going to do? We're going to print out each value in that row. But I want to make sure they're all spaced evenly and there's nothing between them. And so we'll go out of our way to put one space between each value. And we'll go ahead and say system.out. We won't use println because we want them next to each other. So we'll put a space. We'll attach our value. Now, if I'm in the matrix at row R and column C, what is the value that I want? I use my bracket notation, so matrix at row R, column C. And then I attach my second space, so that'll give them a space between them on both sides. And I think that should be good for what we want. And then, of course, at the end of this row, we must print a new line so that our cursor goes to the next line. So that should be enough. And what I do want to do is I also want to add bars to the side. So let's go ahead and print out a bar next to them. So this one will be print without an ln, and we'll do this. The bar, I mean the pipe key, which is like the OR symbol or part of the OR symbol in Java. And we'll do the same thing here. We'll put a OR symbol. And let's see what this looks like. So now we can go to our main and call this method to generate the identity matrix, and then call this method to display it. So here we go. We'll go ahead and say is equal to, and we'll call our method, our gen identity method, and we'll say 3, right? Because we did a 3 by 3 in our example in our drawing, and so that's a two-dimensional array. And then let's print it out. So now we could say print matrix, and we can pass the identity matrix, and let's see what happens. Give it a moment to compile, and we should see a nice output. Oop, that's taking a little bit long. There it goes. And there it is. Right? 1, 1, 1. And so now let's try with the bigger number. Let's do something like 6. So a 6 by 6 identity matrix. Just taking quite a while. I guess my computer's being slow today. I don't know why it's doing this, but let's... And there it is. So a 6 by 6 identity matrix. 1 and 5 zeros, and then a 0, a 1 and 4 zeros, and so on. So our identity matrix method does seem to work. Now let's do something a little more interesting. That takes a little bit more thought. Let's go back to our drawing. In this example, and I'm going to go ahead and see if I can erase this. We'll erase this quickly. Okay, that's our identity matrix. And let's say something. We're going to do what's called transposition. Transposition of a matrix says take every row and make it into a column, and every column and make it into a row. So if we were to transpose this matrix, then the result would be that every row, 1, 2, 3, and every 4, 5, 6 would become a column. So if I were to redraw this, then this first row would be a column, so 1, 2, 3, and then this row would become a column, 4, 5, 6. Or we could interpret it as every column, 1, 4 becomes a row, 1, 4, 2, 5, 2, 5, 3, 6, 3, 6. And if we did this one, transposition, it's the same idea, but this one, since this one is originally 3 by 2, it's going to become a 2 by 3. This one was 2 rows by 3 columns, and it becomes 3 rows by 2 columns. The transposition flips columns and rows. And so this one would end up as, let's do this one. It would be, the first one would be 1, 4, 3, 1, 4, 3. The next one would be 2, 7, 2. Right? So the first row becomes the first column, the second row becomes the second column, the third row becomes the third column. And so that's what transposition does. So let's make a method that, given a matrix that is rectangular, again, we're not going to worry about jagged arrays, but our matrix is rectangular. It doesn't have to be square, so it could be 2 by 3 or 5 by 7 or 4 by 4. It could be square, and transposes it to its transposition version, which is basically the rotated version. So let's make that method. To notice it, I'm going to put up the indices. Let's see if we can spot the. So 0, 1, 2, 0, 1, and then 0, 1, 0, 1, 2. If we were to pick the 1 value, what indices does it have? 0, 0. When we transpose it, where does it end up? 0, 0. Okay, that's not really clear. I mean, it seems to be in the same spot. Let's pick 0, 1, which is the 2 value. Where does it end up? At 1, 0. Let's pick the 5 value. It's at 1, 1. Where does it end up? At 1, 1. So that one's still not clear. Let's do one more. The 3 value is at row 1, column 2. Where does it end up? Row 2, column 1. So if we look at that pattern, so if we saw this pattern of 0, 1 became 1, 0, and then we look at this pattern of this one, sorry, we can do the, no, not the 5, the 6. 1, 2, so 1, comma 2 becomes 2, 1, right? And we did the 3 was at 0, 2, and it became 2, 0. So if we look at the pattern, whatever our row is, it becomes the column value. Whatever the column value is, it becomes the row. So that's the solution we're going to use to make this method work properly. We're going to flip those based on this idea. So let's make that method. Public static. And again, instead of editing the original, we can't, because we can't change the length of the rows and the columns, but we can make a new array that has the correct transposed version. So if this one was a 2 by 3 matrix or 2D array, this one will be a 3 by 2. So let's do that. And so our return type will be an integer 2-dimensional array. We'll call it transpose. And let's go ahead and do. We accept a matrix value, and we will return one. So the first step, just like before, is in order to give our answer, we must generate the structure to hold it, which is a 2-dimensional array. And we will call it transpose. And let's go ahead and make it a new 2-dimensional array of values. And again, how large is it? If this one is n by m, this one should be m by n. Unfortunately, they're not easy variables like m and n. We have to come up with the values. So we need to say, okay, well, the rows of this one becomes the columns here. So how many rows are in matrix? Remember, if matrix is an array of arrays, if we say matrix.length, we are saying how many subarrays are there. That's the same as saying how many rows. So matrix.length is the number of rows, so that should become our column. So matrix.length. That's the first value. That's the row becomes the column. And then what would the column length be in this matrix? Assuming it's rectangular. We're allowed to make the assumption that it's rectangular. With that said, if we also assume it's at least one row, which really I think that's not unreasonable, then we could say if we look at the first row and look at its length, that's how many columns there were. So that can be the new row length. So we're going to go ahead and say matrix at position 0, and then get its length. So if this was 3 by 2, this has now become 2 by 3. So this is the transposed version of our matrix, except now it's empty. Now we have to go and take all the values from the original matrix and put them into the transposed matrix. And that's the work we need to do here. So in this case, I think we do need 2 nested loops because we need to know which row and which column we're in. So we'll say if we're in row R, at index R, and R is less than matrix.length, and R goes up by 1 each time. And again, notice the pattern is almost always the same. There's not always a definitive pattern, but this is a pretty common one for 2-dimensional arrays. And now let's go through every column. Remember, we're saying go to the rth row and get its length. That's how many columns there are. And then we go up by 1 every time. And again, what we just said was, according to this example, if we're in row R, it becomes column R, right? So row 0 becomes column 0. If we're in column C, that becomes row C, right? So let's flip them. So we're going to say the transpose, which is what we're filling in, at, and this is where the reverse happens. If we're looking at matrix at RC, we're storing it in transpose at CR. This is the trick to this problem. We're putting it in the reverse thing. We're retrieving the original from R and C, and we're putting it in C and R. There's the trick. These are the transposed versions of each other. And then the result, when we're done with this loop, is to simply return that new object. And there it is. Now, how can we test this? Let's make a literal two-dimensional array. We can literally create a two-dimensional array that represents this one, and then we can transpose it, and we should get this one. We can do the same for here as well. So let's try that out. Let's go to our main. And let's make a literal two-dimensional array. And we'll call it original. And we'll do a literal 2D array, and we'll do it in a nice format. And we'll say the original is 1, 2, 3. And then on the next row, we'll go ahead and do, oops, I don't know why I didn't, okay, I guess it's being silly. And then we'll do 4, 5, and 6. And so there's our two-dimensional array, 2 rows by 3 columns. If we transpose this, we should get 3 rows by 2 columns. And here we go. Let's go ahead and do this. We'll say int, and we'll call it tr for transposed, and we will say transpose the method, the original, and that should flip it, and then let's print out the original and print out the transposed. So we'll call print matrix on the original, and then we'll print out maybe an extra space just so there's not all crammed next to each other, and then let's print out the transposed version, and there it is. And let's see what happens. And there it is. And I should have put a println. We should have put a println here just to give us a little bit more space. And there it is. So there's our identity matrix, and then there's our original, and there it is transposed. And so notice that it is originally 2 by 3, and now it is 3 by 2. I'm sorry, yeah, 3 by 2. 3 rows by 2 columns. And this was originally 2 rows by 3 columns. Right? And so this is a very useful method. I think matrices in math, even though you may have not used them actively, they do have a lot of really powerful uses in advanced mathematics, and programs that manipulate matrices are very, very important. And so this idea of a two-dimensional array is very convenient for this type of problem. Right? And in fact, there are 3-dimensional transpositions of 3-dimensional matrices, and that's a very complex topic in linear algebra, but it is also very helpful for graphics programming. And so if you ever find yourself in that situation, you will probably use this in some application, this idea of transposition or multiplying matrices and things like that. We could come up with methods that would make that happen. But we'll stop here for this video, and hopefully we can see the takeaway is not necessarily the matrix idea, but the idea that 2D arrays can be inputs just like any other object. And they can be return types just like any other object. Arrays are objects, and they can be generated dynamically as local variables and returned so that someone can manipulate those values in our main. Right? They can be passed in, and they can be printed, they can be stored, values can be created. There's kind of no